Welcome to the Deep Dive. We're here to break down the key insights from the latest research, helping you stay ahead. Today, we're tackling something pretty big, the paper on Ring 1T open weights. It details the first open source reasoning model that's actually been scaled up to 1 trillion total parameters, which is huge. Our goal here is really to unpack the new methods, the breakthroughs they needed to actually pull this off. Because training these massive mixture of experts models, these MOE models using reinforcement learning, it's notoriously unstable and incredibly expensive. Okay, so for anyone needing the quick version, the sort of 1-minute rundown, here are the absolute key takeaways. First, the model. Ring 1T is the first open source MOE hitting 1 trillion total parameters, though it's 50 billion active per token. And it's getting state-of-the-art results among open source models on some really tough benchmarks. Second, the results, highlights. 93.40% on AME 25, 86.72% on HMMT 25, and maybe most impressively, a silver medal level result on the IMO 2025 math competition using just natural language reasoning. No code, no solvers.
Plus, it snagged the highest CodeForces rating, 2088, beating all other models they tested, open or closed. And third, the innovations, how they do it. Three main things working together. One, IcePop, an RL algorithm that tackles that catastrophic train-inference mismatch by clipping tokens that show too much discrepancy. Basically, it stabilizes things. Two, C3PO plus. This is a scheduler for rollouts, budget controlled that makes training much more efficient, especially for those long reasoning chains. Three, ASystem, a specialized high-performance asynchronous RL framework. Think of it as the operating system needed to handle training something this massive, keeping it stable and fast. So that's the nutshell.
Yeah, and that 1 trillion parameter number, it's not just big, it's a threshold. Up until now, that kind of scale, especially for these thinking models that need complex RL for problem solving, that's mostly been the playground of, the big closed source players.
Right, because the costs and the instability just explode as you get bigger.
Exactly. The computational cost is one thing, but the training instability, it's a nightmare. Particularly with MOE architectures, because the way they dynamically route tokens can make any small mismatch between training and inference just blow up.
So Ring 1T, built on their Ling 2.0 architecture, is the one that finally cracked it for open source at this scale using RL. Let's talk about those benchmark scores, though, because they really paint a picture. Who are they comparing against?
They put it up against some strong open source contenders like Qwen3 235B, Atom 2B thinking, and DeepSeek v3.1 terminus thinking. But they also showed results next to leading closed models, specifically Gemini 2.5 Pro and GPT-5 thinking, just to give a sense of where it stands overall.
Okay, so those math scores, AAB and HMMT, clearly put it at the top of the open source pile. But that IMO result, achieving silver medal level at the International Mathematical Olympiad, that's seriously impressive for an AI.
It really is. And the specifics matter here. It solved 4 problems cleanly and almost got a 5th one, problem 2, in just one go. And the key thing, like you mentioned, is how it did it. Purely natural language reasoning. No calling out to symbolic math engines, no generating code to run proofs. It reasoned it out internally. That tells you a lot about the depth of its reasoning capability.
Okay, and then there's the coding side. That CodeForces rating, 2088. You said highest overall?
Yep, highest across all the models they benchmarked. It edged out the next best open source model, DeepSeek v3.1, which was at 2073. So a solid 15-point lead there.
What does a 2088 rating actually mean in practical terms?
Well, on CodeForces, that puts it squarely in the expert category for human competitive programmers. It's a very strong signal. It means the model isn't just good at specific tasks, it has a kind of logical fluency and robustness needed for complex problem solving and planning.
And does that robustness show up elsewhere, like in how well it behaves?
Seems so. They also reported strong alignment scores, an 81.59% win rate on Arena Hard version 2, for example. That suggests they managed to balance pushing that raw reasoning power without completely sacrificing safety and helpfulness. It's a tricky trade-off.
Absolutely. Okay, so given those results, the big question is how? How did they actually manage the training? Let's walk through that 3-stage pipeline they described, starting from the Ling 1T base model.
Right. It's a structured approach. Stage 1 is long chain of thought supervised fine-tuning, or long cut SFT. This is really about building the foundation, teaching the base model how to follow and generate long, complex lines of reasoning, step-by-step thinking.
And the data for that can't just be random web text, right? It must be specialized.
Oh, definitely. They curated it very carefully. A mix of open source data sets, stuff generated by human experts, and even synthesized data from other large models. The focus was clearly on domains requiring reasoning. Math was the biggest chunk, about 46%. Then STEM subjects physics, chemistry at 26%, and code at 20%. The rest was others.
Interesting breakdown.
And crucially, they ran it through a really strict cleaning process. Deduplication, filtering harmful content, of course, but also, really importantly, decontamination against benchmark data. They wanted to be sure it wasn't just memorizing answers to the tests.
Makes sense. And they mentioned training this stage with a 64,000 token sequence length.
Yeah, which is pretty long. That gives the model a large window right from the start to learn those complex multi-step reasoning patterns needed for chain of thought.
Okay, so that's the foundation. What's stage 2?
Stage 2 is reasoning RL. This is where they really sharpen the model's logic skills using reinforcement learning, specifically RLVR reinforcement learning from verifiable rewards.
Verifiable rewards. So rewards based on things you can objectively check.
Exactly. Math problems where you can verify the answer. Code generation, where you can run test cases. Science problems they reformatted into question answering where answers could be checked. They even did organic chemistry using an image analysis pipeline to verify molecular structures. So the policy, the model strategy, gets refined based on whether it actually gets the right verifiable answer.
Got it. And then the final stage, stage 3.
Stage 3 is general RL, and this uses RLHF reinforcement learning from human feedback.
The human alignment part.
Precisely. The goal here isn't just raw performance anymore. It's about recalibrating, taking that powerful reasoning capability from stage 2 and making sure it's aligned with human preferences, instruction following, safety, even things like creative writing. It's about making the genius usable and safe.
Okay, that pipeline makes sense. Build the foundation, sharpen the core logic, then align it. Now let's get into the really innovative stuff, the algorithms that made training at 1 trillion parameters possible. RL at scale is famously unstable, right? Especially with MOE models. So let's start with how they tackled stability. IcePop.
Right. IcePop addresses what they call catastrophic training-inference misalignment. It's a known problem, but it gets way worse with these huge MOE models. You essentially have 2 different computations happening for token probabilities. One during the live generation, the inference or rollout phase, and another during the training phase where gradients are calculated.
And those 2 calculations can drift apart.
Exactly. Tiny numerical differences, maybe different hardware optimizations, or just the stochastic nature of MOE routing. It all adds up, and this discrepancy, delta, can compound over time. The paper even gives a formula showing it can grow exponentially, delta plus 1 GIC, 1 plus mood GIC.
So like steering a giant ship with 2 compasses that are slowly diverging. Eventually, you're way off course or worse.
That's a good analogy. And IcePop is like an advanced stabilization system. It's technically a variant of GRPO, Generalized Relative Policy Optimization. What it does is use something called double-sided masking calibration.
Double-sided masking. How does that work?
It basically sets a trust zone for the gradient updates. They define a lower bound alpha and an upper bound beta. For the reasoning RL stage, these were set to 0.5 and 5. Any gradient update where the probability ratio between the training and inference policy falls outside the zone, meaning the discrepancy is too large, is considered noisy and is simply masked out. It's ignored, popped out during the optimization step.
So you're only keeping the gradient updates that are, let's say, well-behaved within an acceptable range of deviation.
Pretty much. It stops these potentially huge, unstable updates from derailing the training process, keeping things smooth, without actually having to slow down the inference calculation itself.
Okay, that makes sense for stability. But throwing away gradients, are you potentially losing something important? Like maybe some of those high discrepancy updates were actually pointing towards the really novel or creative solution, even if they looked noisy?
That's a fair question, always a concern with clipping or masking techniques. Are you just dampening noise, or are you suppressing useful exploration? The paper argues the stability gain far outweighs any potential loss here. They showed empirically on a smaller test model called Ring Mini 2.0 that IcePop not only stabilized training where a baseline method failed, but it also led to a big performance jump, over 14% gain on AME 25 compared to the base model without this stabilization. So it seems crucial for enabling learning at this scale.
Okay, stability handled by IcePop. What about the other big hurdle? Efficiency, especially with those really long reasoning chains, the chain of thought stuff. That sounds computationally expensive for RL.
Yeah, that's where C3PO++ comes in. The problem is resource idleness during the rollout phase of RL. Imagine the model is generating a complex math proof that takes thousands of tokens. While it's doing that, the GPUs doing the optimization calculations are just sitting there, waiting for that long sequence to finish before they can update the policy. It's very inefficient.
So C3PO++ tries to fix that waiting time.
Exactly. It uses what they call budget-controlled rollout partitioning.
Okay, how does that budget work? Is it like a time limit?
It's a token budget, FDII solves. They generate rollouts in parallel across many GPUs. As soon as the total number of tokens generated across all active rollouts hits this budget and call, they stop generating and immediately run the optimization step.
But what about the sequences that weren't finished? The long math proof that was only halfway done.
That's the clever part. They don't throw them away. Those unfinished rollouts are buffered. Then, in the next iteration, after the policy's been updated, they resume generating those sequences right where they left off using the new, improved policy. They call this batched continuation.
Resuming with an updated policy mid-sequence.
Mm-hmm.
Does that cause any issues? Like inconsistency in the reasoning chain?
You might think so, but apparently not significantly. The benefit of keeping the optimization pipeline constantly fed with data outweighs any minor inconsistency from the policy shift. They also have a mechanism to discard rollouts that get excessively long, using a retention threshold, sigma, just to prevent memory issues. And importantly, they showed this works. The reward curve stayed smooth, and the final performance on benchmarks like AME25 and CodeForces was basically identical to the baseline method that didn't use C3PO++ way. For CodeForces, it was 2088 with C3PO++ versus 2084 without. So same quality, much faster.
Right. What was the speed up?
They reported roughly a 2.5 times speed up just for the rollout part of each step.
Wow.
Yeah, and that translated to about a 1.5 times speed up for the entire end-to-end training step. When you're training for weeks or months on thousands of GPUs, that 1.5x is absolutely massive. It makes the whole project feasible.
Okay, so IcePop for stability, C3PO plus for efficiency.
Yeah.
But you still need the underlying infrastructure to run all this at trillion parameter scale. That's where ASystem comes in.
Exactly. ASystem is the specialized framework. Think of it as the distributed operating system designed specifically for this kind of large-scale asynchronous MOE-RL training. It's built on a single controller plus SPMD architecture co-designed with the algorithms.
And it targets specific bottlenecks that regular frameworks would choke on.
Right. They highlight 4 key components.
Oh, okay. Let's quickly run through them. What's the first one?
First is the hybrid runtime. Normally, you might have separate systems or clusters for training and inference. Moving massive amounts of data back and forth is a huge bottleneck. The hybrid runtime basically unifies these, allowing training and inference workloads to run efficiently on the same infrastructure, cutting out that data transfer overhead.
Makes sense. Second component.
This is all about GPU memory. Training these huge models constantly runs into out-of-memory, or OO errors. is their custom GPU memory management library. It uses techniques like memory switching and unified memory pooling to be much smarter about how memory is used, allowing for larger batch sizes and fewer OM crashes.
Critical for stability and throughput. Okay, third.
A state. This tackles weight synchronization. When you have a trillion parameters spread across potentially thousands of GPUs, and the policy is constantly updating, how do you make sure the inference workers are always using the very latest version of the model?
Yeah, that sounds like a nightmare.
A state uses a very efficient, zero redundancy, peer-to-peer transmission method. They claim it allows sub-second synchronization of the entire trillion parameter model. Super fast, ensuring the inference is always based on the most up-to-date policy.
Impressive. And the last one? A sandbox.
Right, a sandbox. When you're doing RL with verifiable rewards, especially for things like code generation, you need to actually run the code or execute the solution to check if it's correct. A sandbox provides very fast, isolated environments, like little virtual machines, to do this validation safely and coldly. They mention a 100 millisecond startup speed, which is crucial so that validation doesn't become the new bottleneck.
Okay, so you got the stable algorithm, IcePop, the efficient scheduler, C3PO++, and the high-performance infrastructure, ASystem. It all fits together. But even with all this, no system is perfect. What limitations did the paper itself acknowledge?
They were pretty upfront about areas for future work. One major one is still inference efficiency. While the training is now feasible, running inference on a one-team MOE model, especially one that generates long internal thought processes like Ring1T does, is still computationally expensive. It uses grouped query attention, GQA now, but they suggest exploring things like mixture of batch attentions, MOBA, or maybe advanced linear attention methods to make inference faster and cheaper.
And the stability issue. IcePop solved it, but is it completely gone?
Not entirely. They mentioned that even with IcePop mitigating the effects, the underlying cause, these subtle numerical discrepancies between training and inference hardware or software operations still exists. It's a persistent, low-level source of potential instability. Fully solving that might require even deeper hardware-software co-design in the future.
Okay. And what about the model's actual capabilities? They focus heavily on reasoning,
Yeah,
right?
exactly. Which means other potentially desirable skills are currently, as they put it, under-optimized. Things like advanced agentic behavior, using tools effectively, complex multi-step planning, interacting with external systems. These weren't the focus of this training run. They see Ring 1T as a very powerful base model, but future work will need specific agentic RL training to build out those kinds of capabilities.
Right, makes sense. Focus on one hard thing first. So let's try and wrap this up. What's the big picture takeaway here for you, the listener?
Well, Ring 1T really feels like a validation. It shows that, yes, open source models can be scaled effectively to the trillion parameter level for complex RL tasks, provided you tackle those core challenges of stability and efficiency head on. Absolutely. The combination of IcePop, C3PO++ add, and ASystem isn't just an engineering feat. It's a demonstration that breakthrough performance on really hard competition-level reasoning tasks like that IMO silver medal is now within reach for open source efforts. It helps level the playing field, closing the gap with proprietary systems in these critical reasoning domains.
It's a really significant step for the open research community. Okay, before we finish, here's something for you to think about building on what we discussed. We talked about IcePop achieving stability by masking out gradient updates from tokens that showed excessive probability deviation between training and inference. It filters out the noisy or unstable updates. So the question to mull over is, by systematically removing these high variance updates, the ones that deviate the most, could this mechanism, while boosting logical stability, also inadvertently prune away some of the model's potential for true novelty or diverse, out-of-the-box creative reasoning? How might this filtering shape the kind of intelligence that emerges, even as it becomes more stable and predictable?